So again, here is our solution. And let's investigate its asymptotics at large values of x. So first of all, we have a look at our exponent. And the natural step is to look at the possible saddles of this exponent. So here is the equation for the saddles. And let's see what's happening. Suppose x is positive. Then our saddle is positioned at negative values of t. Now let's figure out the steepest descent direction. The argument of the second derivative is 0. So the steepest descent direction is obviously pi by 2 plus pi n. The vertical one. And let's actually draw the whole picture of stationary phase line. So this is the first stationary phase line, and the second one is the steepest ascent direction, which is perpendicular to the steepest descent direction. And as you see, this line arrives at the origin at the point where our contour starts. Keep in mind that the steepest ascent direction from the saddle is the steepest descent direction from the end point of our contour. So what we conclude is that there is no way one can define the contour so it passes through the whole saddle, like from minus I infinity to plus I infinity, because we start here. So our only choice is to deform the contour along the stationary phase line like that, like a right angle. Actually, there is a subtle way to take into account both the contribution from the end point and the contribution from the saddle. But we are interested in the leading contribution right now, so we won't dwell into that kind of subtleties here. And it's quite obvious that the leading contribution comes from the end point of our contour, or the beginning point of our contour, I would say. So let's see how this comes about. Well, first of all, for small values of for small values of t, if t is of the order of 1 over x, x is large, their integral is accumulating its value for these values of t, and we could discard the quadratic term. Indeed, because when t is of the order of 1 over x, the first term is of the order of 1, and the second term is of the order of 1 over x squared, so can be safely discarded. This way, the whole integrand is simplified, and the asymptotics is defined by the following simple expression. Oh, sorry. So from 0 to actually to minus infinity. Why minus infinity? Because the integral is convergent in the for x t of the order of 1 over x. So we kind of, keeping this in mind, we expand this contour into their semi-infinite, continue this contour into a semi-infinite segment from 0 to minus infinity. And the integral is elementary and is easily taken, yielding the answer minus square root of 2 over pi 1 over ix. And of course, the saddle give the contribution of the order, so the saddle position at point t minus equals minus x. So f of minus x is equal to minus x squared by 2. So the saddle contribution leads to the following exponentially suppressed factor, comparing to the power law behavior for the contribution from the endpoint. So hence, this is the leading one. And here we are. So in complete analogy, for x, for negative x, the whole procedure goes in the same way, but like a mirror symmetry. So for x negative, the saddle would be here, and the contour deformation would go symmetrically into the right-hand side. So this is a universal asymptotics for our second linear dependent solution. And that is precisely the power law behavior we expected to get from our initial condition in our solution of this differential equation. So here it is. So I hope you saw all the subtleties, and hopefully you will solve your home exercises without any trouble.